Howdy, folks. Hello again. In this video, we're going to take a look at um, experimental data that would be modeled by exponential, logarithmic, um, or logistic curves, logistic functions, log functions, and exponential functions. So earlier, we took a look at some situations where um, the situation itself just warranted one of those functions, like compound interest, for example, or like like converting um, sound intensity to a number of decibels that involves log functions. But what we're going to take a look at this time is actual experimental data. So data is collected, and then when we look at a scatter plot, if it resembles one of these functions, we can ask technology to find the best fit curve, the curve of best fit. A regression curve is often what it's called. So we're going to look at data that experimental data that would best be modeled by an exponential or a log or a logistic function. So let's look at this first situation. It's going to look a little familiar. So suppose $20,000 was deposited into an account 6 years ago. The data in the table below represent the value of the account at the beginning of each year for the last 7 years. So at the very beginning, there was $20,000. So at the very beginning, there was $20,000 in the account. And at the beginning of the next year, there was $21,516 in that account. And the beginning of the year after that was $23,355 in the account, so on and so forth. So it's clearly earning interest. Its value is increasing. So since all we know is the initial amount and how long it's been sitting in there, we have some data. So we're going to ask, we're going to use technology to create a scatter plot so we can take a look at what shape this relation takes when graphed on the XY plane. And then we're going to ask technology to fit a curve to it. And then we'll use that curve to answer some questions. So again, you can use any software you feel comfortable with. I'm going to use GeoGebra because I'm comfortable with it. Desmos is fine too if you want to go that route. Or if you know how to use a graphing calculator to do this, feel free. But I'm going to show this using GeoGebra. So first thing we got to do is type this data in to this, on GeoGebra, you type it into the spreadsheet part here. So that first column, we have your 0, 1, 2, 3, 4, 5, and 6. And then the values at the beginning of each year. I'm not going to make you watch me type these all in, so I'm going to go ahead and skip ahead. Okay, so I've got all the data typed in, and then now I wanted to create a scatter plot. So I'm going to choose both sets of data here, go to my histogram, choose 2 variable regression analysis, and it's going to make a scatter plot. You could make the argument that this is linear, that the money is growing at a constant rate. Maybe it is. We're going to go ahead and fit an exponential since we've seen typically if compound interest is involved, it's modeled by an exponential function. So we're going to go ahead and fit an exponential curve to it. So down here where it says regression model, we're going to go put exponential, and it's going to fit an exponential curve to it, and then we're going to need that curve. It's right down here. Now remember, this is the curve of best fit, meaning not every single data point is going to be, is going to be on the curve. Again, without going into the calculations involved, basically what's going on here is the technology is trying to find the curve that minimizes how far off each point is. So like that curve, if you were to find the distance between this curve and this line, or this point in this curve, 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 if you were to find those distances and add them up, you're looking for the curve that would minimize that sum is kind of what's going on. Again, we're not going to go into too much detail on how it does that. That's not the purpose of this lesson nor this course. So, okay, now we're going to use this information to answer a few questions about this data set. So let's go back to part A. Using technology, create a scatter plot for the above data where the account value is the dependent variable y, which we did. B, using technology, find an exponential function for the data. We have that too, so we'll go ahead and make note of that. All right, so B, find an exponential function for that. So it's going to be, I'm going to go ahead and use the letters we're used to. So I'm going to say A of t and all that good stuff. So it's going to be A of t. So the amount is a function of time, 19,820. 0.4305 E 0821 T. I think I got that copied down right. Okay. Part C, write the function in the form which we've already got, so we're good. So part C, we know that the initial amount, again, this because it's experimental data, we know the initial amount was actually 20,000. But when it fit when it found the curve of best fit, the curve of best fit has the initial value of the account being 19,820. So again, this isn't perfect. It's not a perfect solution for modeling this data. There's other ways to model the data that you can make arguments for a little bit better. Just one option we have. And K, our growth rate here is 0.0821. D says graph the curve on the scatter plot. We already did that. That's done in GeoGebra or whatever software you're using. E, use the model to predict the account value after 10 years. So the amount after 10 years is going to be 19,820, 4305 e to the 0.0821 times 10. I'm going to run this through a calculator. 457.31. So just over $45,000 in the account after 10 years. So it's earning a pretty high percentage of interest. That's the annual interest rate is pretty good. If in only 10 years, you've more than doubled. Okay, so again, this is merely showing us that if we have some data that we feel is exponential in nature, we can ask technology to fit a curve to that. And if you're interested in how the technology fits that curve or the mathematics behind that, there are courses where you can go into that in detail. You can go as deep into statistics as you want. Let's go take a look at another one here. We got a meteorologist is interested in finding a relation between the height of a weather balloon in kilometers and the atmospheric pressure in millimeters of mercury on the balloon. The meteorologist collects the data found below. So basically, as you release a weather balloon, as it goes up and up and up and up in the atmosphere, what's happening to the atmospheric pressure? How are those related? The height of the balloon and the atmospheric pressure. So they ran an experiment. Here's the data that they were given. Part A says use technology, create a scatter plot using this data where height is the dependent variable. So height is y, what we would call y. Again, I'm going to use GeoGebra for this. I'm going to type it in the spreadsheet. I'm not going to make you watch me type this in, so I'll skip ahead to where I've got it typed in. Okay, so here we are. We got our data typed in. So at ground level, the atmospheric pressure is 760 millimeters of mercury, and then 2.2, well, it's rounded, but 2.235 kilometers in the air. The atmospheric pressure has dropped to 550, and then we've got some data in between. So let's go ahead and select both of these columns of data. Choose our histogram, two variable regression analysis. Again, you can make an argument for a linear model if you felt like the rate of change of the height with respect to pressure is a constant rate of change. You can make that argument. We are actually going to fit a log curve to this. So it says using technology, find a log function for the data. So the person running the experiment believes that these two things are related in a way that a log is more appropriate. So let's ask GeoGebra to do that. So I'm going to come over here and go do log. And there's the log curve that passes through there, which we're going to need that. So all right, so let's see what it asks us. It says part A, create a scatter plot. So we did that. B, find a log function. So it's going to be y 45.7863 minus natural log 6.9025. Okay. All right. And then using the I'm going to go and use the variables they had. So this would basically be height as a function of pressure. And then C, graph it on the scatter plot. We already, that GeoGebra took care of that for us. And then D says predict the height of the balloon if the pressure is 560. Whoops, this would not be X anymore since I switched my variables. That'd be a P. So I'm going to plug 560 in. And see what height we think this balloon would be at if the pressure was at 560. Based off the data, we would expect it to be somewhere between 1.8 and 2.2, somewhere around 2 kilometers in the air. But we'll see. We'll see what the model says. We get 2.108 kilometers, which is what we think the height of that balloon would be if the atmospheric pressure was 560 millimeters of mercury. Again, just merely showing us that technology can fit lots of different elementary functions to the data. But again, it requires user input. You have to kind of know how or have some idea of how the data is related to kind of use the most appropriate curve. Let's look at another one. The table below gives the amount of yeast biomass in a culture after T hours. So basically you start with some yeast and let it grow, and then keep track of how much time has elapsed and just kind of keep measuring how much yeast there is. Part A says create a scatter plot. We'll do that on GeoGebra. And then they want us to fit a logistic function to that. Well, let's see what the scatter plot looks like and see if logistic makes sense or not. Again, how do you know to do a logistic? Well, we're talking about a living organism, and chances are that living organism is growing in a very finite amount of space. So there's only so much growing it could do. Um, so the fact that the rate at which it grows would kind of taper off and have a carrying capacity makes a lot of sense. So a logistic function seems appropriate. But again, let's use GeoGebra. Get this typed in. Look at this scatter plot. Once again, I'm not going to make you watch me type this in. All right, here we are. We got it all typed in. Let's go ahead and get our scatter plot. And more so than the other two examples, this pretty well models a logistic curve. Looks a lot like it just as it is. So let's come down to our model and pick logistic. Fairly straightforward. Goes right through those dots. Maybe not perfectly, but pretty close. And then we've got our model down there for us. So let's go answer some questions, see what we're asked to find out. That's part A. That's done in GeoGebra. Part B, we've got our function here. So we got y equals, our carrying capacity is 663,022. We've got 1 plus 715763. Then we got 0.547. As we can see, B is positive. The negative is part of the formula. So this is growth, which we saw in the data. All right, here we go. Let's see, graph it. We did that. GeoGebra handled the graphing part. D, what is the predicted carrying capacity? 663,000. Biomass of 663,022. Never really gives me a unit there. Maybe there aren't units on biomass. That's not something I super familiar with. But that's our carrying capacity, the numerator of that. E, predict the biomass when 19 hours have elapsed. Okay, so Y with 19 plugged into it. We can handle that. That's what calculators are good for. Plug a 19 into that, and let's see what we get. We expect it to be a little bit more than 661, so we'll find out. It's 66157. So the 661, that was, again, kind of predicted that. Again, as far as units go on this, I'm not sure. So I was going to go 661.57. And that's it. So I asked us to do with it. This wasn't meant to be a particularly involved section. It was just meant to show us that in the case where we have experimental data, we can lean on technology to create the model for us. But it needs us to tell it what model is appropriate. So still some human intervention needed here. But other than that, that's all we got.